In 8.3, we're going to be looking at the difference between strong and weak acids and bases. Remember from 8.1 that acids produce, or 8.2, sorry, acids produce protons when they dissociate in water. Bases produce hydroxides. As we're going to talk about in 8.4, we will be looking at specifically pH, which measures the strength of that hydrogen compound, but the two, H and OH, are interrelated because when you dissociate into a solution, what is that solution? Water, H2O. So we're able to work with acids and bases and determine their strengths. A generic equation, HA, which would be your acid, dissociates into hydrogen plus, that is what we measure as an acid itself, and an anion like chlorine or so on and so forth. On your product side, this is what we call a dissociated form of an acid. On your reactant side, this is what we call an undissociated form. Depending on strong and weak acids, will determine where in this equilibrium reaction do we lie. If you're a strong acid or base, the equilibrium lies to your products. So if we have HCl, which is a strong acid, we do have an equilibrium where it dissociates into hydrogen and chlorine ions. But as you can see, that equilibrium arrow strongly favors the product side. Therefore, when we're looking and representing strong acids and strong bases, we just use a straight arrow instead of an equilibrium arrow, showing and assuming we have what is called full dissociation. Looking at a base, NaOH, sodium hydroxide, is also a strong base. So it dissociates into a sodium ion and a hydroxide ion. Because it's strong, we therefore assume full dissociation, and we use a straight arrow, representing that we make all sodium and hydroxide ions. Now the strength of an acid or a base is the measure of the dissociation that is occurring, because our pH probes specifically measures hydrogen ions, so the presence of hydrogen being present. Therefore, hydrogen is the dissociated form, and that is what we're directly measuring, and so that is what the pH or strength of an acid is. Do not confuse strength with concentration, because you could have a very weak concentration of a strong acid and it still have a lower pH than a high concentration of a weak acid and or base. What if it's a weak acid or base then? So if it's a weak acid or base, the equilibrium lies to the reactant's side. So the reactants are being favored. Here we have CH3COOH, acetic acid, or ethanoic acid, depending on what you want to call it. The arrow is favoring the undissociated, so these reactions, we say, stay at equilibrium, and so we assume equilibrium is present. We don't say the reaction doesn't just take place, because with the pH probe, we can still measure hydrogen ions present in the solution, but they're at much lower values than in a strong acid. Therefore, we have more of the original acid itself, CH3COOH, present in solution and not the actual hydrogen ions. For our base, here we have NH3 and we react with water, and you create NH4 plus and OH minus. Again, being a weak base, we will have more NH3 present than we will have NH4 plus or OH minus. Now, what are we measuring here? We are measuring the acid, or what's called the conjugate acid, as we learned in 8.1. NH4 plus, that has that extra hydrogen, and so that's what we're going to be able to measure that acid with. Again, it would have an extremely high pH because it's really not present, but it is there. What does stink about acids and bases is there's no general trend of what's strong and what's weak. You straight up have to memorize the strong. Once you memorize the strong, everything else is considered weak. There are 3 strong acids: HCl, or hydrochloric acid, which you should know and have used many times. HNO3 nitric acid. I personally have never used this. It is an extremely dangerous acid and extremely strong. H2SO4 sulfuric acid, which you have used as well. We have 4 strong bases. There is a small trend here. If you look at the metals, we have lithium, sodium, potassium. Those are all alkali metals. And bases are also referred to alkaline solutions or alkalis. And so you can guess where that comes from. So we have Ba, which is an alkaline, and our alkali metals, and not all of them make strong bases, but there's a slight trend here. The 4 that we use, or the 4 that are strong, are sodium hydroxide, lithium hydroxide, potassium hydroxide, and barium hydroxide. Any other acid and or base present is weak if it's not on this list. Some examples being is CH3COOH, ethanoic acid, or any other organics, H2CO3 carbonic acid, or H3PO4 phosphoric acid. As we saw, NH3 is a common weak base, ammonia. Also, other amines like C2H5NH2, ethylamine. Any amine is also a base, as amines, NH2s, are just an organic derivative of NH3, so on and so forth. How do we distinguish between strong and weak acids and bases then? Well, we know, or we assume, strong acids and strong bases go to full dissociation. Therefore, they're going to contain more ions in solution than a weak acid and or base. So there are actually 2 tests in which we can run, and 1 we can observe in order to test the strength of an unknown acid or base. Looking at electrical conductivity. Electrical conductivity depends on the concentration of mobile ions. So the key word there are ions. Electricity runs via charge. The charge that is present is the dissociated form, or the ions present in a solution. Therefore, we know strong acids and bases fully dissociate. Therefore, they have an increase in their conductivity. And weak acids or bases decrease that conductivity because they have less hydrogen ions present. pH. As discussed in 8.4, pH is the measure of hydrogen concentration. What it does is a direct comparison of the strengths. The higher the pH you have, the lower hydrogen ions present. So if you are a strong acid, you are going to have a low pH, closer to the 0, 1, 2 range. If you are a weak acid, you're going to have an increased pH because you have fewer hydrogen ions present in the solution. We do have a scale called pOH, which is the inverse of pH, to work with bases. But we can make the assumption of working with an inverse that the base is strongest at the highest pH and weakest at a lower pH, so on and so forth, once you've reached that level of 7. That will be discussed a little bit more in 8.4 and in much more detail in the HL topics. We could also look at rate of reaction. This is not something you can quantify, but you could visually see, and it's really important to know when you're running a reaction what type of reaction you're going to run, so you know the strength of that reaction. If you're a strong acid or base, you're going to increase your reactivity. And so you know when working with strong acids and bases, there are certain things in which you can react with in order to stay safe, or what would be more of a dangerous situation in which to interact.